Hello and welcome. So in this lecture we will see an important topic, which is learning in parametric models. So in a typical machine learning context, we want to map the given data into an output through a function, right? So if I denote the output as y, so we have a mapping function which maps the input data to output, right? So this basically we call this as a model, right? And this model, we can have two types of models. One is parametric model and non-parametric model. So in the case of so basically this model or the function will have a set of parameters associated with it, right? So a set of parameters associated with the model. And in the case of parametric model, basically these set of parameters are fixed. So this is fixed number of parameters, right? For example, in a linear regression example, so you learn a curve something like y is equal to mx plus c, right? So these coefficients and the parameter c. So basically we have two parameters here. So m represents all the coefficients of the function that you have learned, and these are fixed actually. So once you come up with this model, right? So whatever data points, in additional data points that you throw on this model, so model is not going to change, right? Model will remain same. So that's why we call the parameters are fixed. So this is called a parametric model, right? Or we basically start with an assumption on the model, right? So because in this case linear regression, basically our assumption is the model will be behaving as a linear model, right? So in contrast, in non-parametric model, basically this will be a complex model. So here you will have a lot of parameters, and the model will be very complex, right? So that is basically called a non-parametric model. So it doesn't mean that in non-parametric model you don't have any parameters. That is wrong. Basically you will have more number of parameters in the case of non-parametric model, and it will be very complex in nature, right? So let's stick on to the parametric model for this lecture. So basically we call the model learning, basically model learning is the task of constructing a model from a set of instances. So these are the example data that you have provided to learn the model from the set of instances. Yeah, so this is basically model learning, right? So you are constructing a model with parameters associated with it from set of instances. So in machine learning context, we call this as training data, right? You have training data. From the training data, you learn a model, right? So the learned model will have a particular kind of a functional form or a shape with a set of parameters associated with it, right? So let's consider a simple example to understand what is basically happening. Let's consider the same classic example of tossing coin. So tossing a coin. So so in this case, I don't know whether I have a fair coin or a bent coin. So I cannot just assume that the probability of getting a head is 50% or 0.5. So I don't know the nature of coin that I have. Only observable is the data instances. So what are the data instances? Basically, you observe head or tail, right? So you are generating lot of heads and tails, and that becomes your data, right? So from this data, we want to learn the parameter associated with this process, right? So we can represent this experiment as something called let me use another color. So a notation called plate notation. So a plate notation is something like this. So we associate the random variable. So this basically represents multiple instances of the random variable outcomes that is being generated, right? So this is basically the tosses, right? And assume that this is the parameter theta associated with it. So this is another random variable associated with your experiment, right? So this theta is basically forms a controlling parameter, and basically this is probability of heads. So theta represents the probability of heads, or we can call this as a controlling parameter which determines the outcome of the experiment, which is nothing but tossing of the coin. So x can take on possibly heads and tails, and this theta basically determines the outcome of the experiment, right? So So the each this you can call as multiple copies of the same parameter, same random variable x. So multiple copies of the random variable, the outcome of the experiment. So this is basically called a plate notation, right? So the conditional probability distribution, the CPD, in this case we can represent it as probability of x, the instances I am not I am so these are the copies of all copies of the variable x for all m, right? For all m. So this is taking a value of heads given theta, right? So this is our function form, basically probability of x taking on how many times it takes heads given theta. So this we define it as theta, right? So since we have defined theta represents the probability of heads, so how many times it is going to take heads given theta is again theta, right? So what we are interested is the we can look at this problem as an optimization problem. So we are looking for a theta hat which maximizes the chance of getting the sequences that I have given as examples, right? So theta hat represents the what is the chance of, right? What is the chance of getting the same sequences that I have supplied to this function as input, right? So so let me formalize this problem. So given the data set D, so D I am representing it as x of 1, x of 2 up to x of m, right? So this is the sequence that I have generated. So example data, basically I have m instances that I have generated, right? So basically these are heads or tails, right? So the theta cap or theta hat is basically argmax of the parameter theta of this probability of data given the parameter, right? So this is the parameter for which the data has highest probability. So our goal is to find out the form of or actual value of theta hat, right? So let us consider this with an maybe a small instances of this we can take, and we can see how it will look like. So let us generate. So consider a sequence of coin tosses, right? So let me just take it as a head and tail and heads, right? So consider only M is 5 now. 5 tosses I have considered, right? So let me write the probability of data. So what is data? My data is the first toss is head, the second toss is a tail, the third toss is again a tail, followed by 2 heads. X of 5 is at given theta, right? So what is this? So I have here 3 heads and 2 tails, right? So probability of getting a head is theta, and that of tail is basically 1 minus theta. This is also 1 minus theta. This is theta, and this is theta. So basically I have theta cube multiplied by 1 minus theta square, right? So can you identify what kind of a distribution that we are talking about? So this is you are recording the successes in n trials, right? So what is the probability distribution which governs the number of successes in n trials, right? So if P is the probability, right? P is the probability, and R number of successes, P of R, 1 minus P of n minus R, maybe so this is basically the binomial distribution that we are talking about, right? So this is a binomial probability distribution, right? So in general, so we can we have just seen the one instance, but let us generalize it. So in general so the set D, this is our data instances, D with x of or m of x1, this is the number of heads, and m of x0 is number of tails, right? So the P of data given theta is equal to, so what is this? Theta of m x1 multiplied by 1 minus theta m x0, right? So in the just see that in this example, so why we have multiplied all this? So these are basically, we are assuming that the distribution is IID, independently and identically distributed, right? So our assumption is the data is generated from a distribution which is assumed as IID, independently and identically distributed. So since they are independent, the joint probability can be just a probability of multiplications, right? So P of A comma B, the joint probability distribution is P of A multiplied by P of B. So similarly, we have taken all these as all the coin tosses as independent tosses, since the number of previous outcome will not affect the current outcome, right, or the outcome in the future. So we can multiply this. So that's why we have written like that, right? So mx1 denotes all the instances where we got heads, and mx naught represents that of tails. So we have generalized this like this, right? Now, so we call this as a likelihood function. Likelihood function, right? So I write it as L of theta like this, right? So this is my likelihood function, and usually we will basically represent this likelihood function as a log likelihood function. So this is just for computational convenience. So log likelihood function, I represent it as a L of theta d as log of L your likelihood function, right? So how this will look like? So this will be so since I have taken log, so the exponential part will become a multiplication factor log of theta, and the multiplication factor become the addition m of x naught log of 1 minus theta, right? So this is my log likelihood function. So what is remaining in an optimization problem? We have to maximize this, right? Maximize this log likelihood function. So for that, so basically what we are looking is maximum likelihood estimate, right? So how will you maximize this function? You have to differentiate this part and equate it to 0 and find out for which theta value this function will be maximum, right? So since this is a very simple differentiation, let's see how we can do that. So if I take the dou L of theta, this will be equated to 0, and so this will be m x1 divided by theta, right? And this will be minus of m x naught divided by 1 minus theta, right? So this minus sign is coming from differential of 1 minus theta, So which is this part is minus, so that's why I have given this minus sign here, right? So now let's see. So if you equate it to 0, so this will be so m x1 by theta is equal to mx naught 1 minus theta, right? So this will be mx1 minus of theta multiplied by mx1 equal to theta multiplied by mx naught, right? So this will become so this part goes this side, so this will become plus, so then theta will be mx1 divided by mx naught plus mx1. So this is nothing but our theta hat, right? Because we are looking at the optimized parameter theta. So this is theta hat, right? So this is the optimized parameter that we were just trying to find out, right? So if you plot the log likelihood or likelihood function against the probability values, so this is our probability values from 0 to 1. So this will look like, so this will look like something like this. This will be a smooth curve. Oops. So something like this. So in the 5 toss coin, this will be somewhere around 0.6, right? So that's how we compute the parameters for the model. So in this lecture, basically what we have seen is we want to construct a model. So far in this probabilistic graphical model course, we were dealing with a graph, right? A graph and a probability distribution tables or conditional distribution tables, right? But now we have data instances, and from that we have to generate the structure plus the probability distribution table, right? So basically this is achieved by computing the parameters associated with the function, right? So this is basically called model learning, right? So this finishes this lecture. We will see a general case. So here we have only taken theta taking binary values or theta as success and theta 1 minus theta as a failure parameter, but this theta can be multinomial, right? So it can take multiple values. So how the same theta hat can be computed in that case. So this will be described in another lecture. Thank you.